it is time to start our next unit, which starts on page 121. So we've done exam 1, exam 2. This is exam 3. Maybe I should even, let's see, write this. This is the start of exam 3 material. So in Stat 100, we have 3 midterms and a final. So exam 3 won't have regression or probability or any of the stuff, box plots that we did on exam 2 on exam 3 or exam 1. So the individual exams are not cumulative. And then the final is, but it's kind of an overview of the whole course. People usually do really well on the final. It sounds scary to have a cumulative final, but it's usually not. Usually people do totally fine. So 1022, today is the day. We're starting a whole new unit, like I said. So this is going to be something like we've never done before, but it's the start of something we're going to be doing throughout the rest of the semester. So it's the start of this idea of inference. And what that means is basically we want to use what we get in a sample to estimate what we would get in a whole population. And that's what statistics is. That's like something that happens all the time in the world of statisticians. So chapter 13 is the start of that. And it says statistics for chance numbers. We're going to deal with numbers generated by a chance process. So like sampling, we're randomly picking people. Those are chance numbers. Rolling a die, flipping a coin, all that stuff we talked about with probability, those would be chance numbers. So we're going to look at the statistics for them. And the first chapter, actually, if we look, chapter 13 is short, right? It's only like 2 pages. And the first chapter is just kind of to get you guys used to this idea of uncertainty, sampling, and the chance number idea. So let's start with that. So we're going to talk about this idea of box models, or I like to call them probability models. Because we just talked about probability, why not keep that trend going a little bit? So what box models or probability models are is just that it's a way to represent this idea of a chance process. So it says there's an analogy between many chance processes and drawing numbers randomly from a box. Okay, and adding their sum, taking their average, etc. And so in this chapter, we're gonna start simple. We're gonna first talk about things like coin, dice, roulette, gambling games, things that we've talked about in the past. And then later, we're gonna look at sampling, surveys, polling, all of that good stuff will come the second half of exam 3. But to start off, we're going to talk about simple things where we know, like when we flip a coin, we know exactly all the outcomes and their probabilities. So that's what the probability model or box model is going to show us. What are all the options I can get? And what's the probability associated with it? So I think, let's just jump right into our example. I think the best way to do this is to start with an easy example like the coin. So it says, create a box model for counting the number of heads in 10 tosses of a fair coin. Okay, so this is easy to think about, right? This is even easy to do. If I had a fair coin, I could toss it 10 times, count how many heads I get. We know we're supposed to get 5 heads. We might not get 5 heads. We might get 4. We might get 6. We might get 10. So this model is looking at uncertainty, the uncertainty of flipping a coin. And my hint, it says here, in creating your box model, it's always simplest to make the box for a single draw. So this is the biggest hint with chapter 13, is that we're not going to think about flipping a coin 10 times. Let's just think about doing it once. Because say we were flipping a coin 1,000,000 times. I don't want to think about that. I just want to think about doing that once, and then we can figure out what we're expected to get if we do it 1,000,000 times. So it says a box model is just a box with tickets, so nothing super fancy. If I was going to draw this, here's a box. And if I think about a single draw, a single flip, I can either get a head or a tail. And it says the tickets have to have a number on them. So here, since I am specifically looking at the number of heads, I'm going to count that as 1. And I'm going to count the number of tails as 0. So this box has 2 tickets, and the 1 represents getting a head, and then the 0 represents getting not a head or a tail. And essentially what I'm doing is I'm saying if I draw out of that box once, that's the same thing as flipping a coin. I can either get a head or a tail, and I have a 50% chance of getting either one. So this is saying that if I can say if I draw 10 times out of my box and count how many ones I get, that's the same thing as flipping a coin 10 times. So I'm going to say I'm going to draw 10 times with replacement, because it does say we need to specify whether the draws are made with or without replacement. So we already said how many draws we're making, 10. And then I want to draw with replacement, right? Because every time you flip a coin, you can't take off a side. It's like there's always a head or a tail. So if I get a tail on the first draw, I want to put it back. I can get a tail on the second draw. So I would draw 10 times with replacement and take the sum. And so the idea is that this simulates flipping a coin 10 times. Flipping a coin 10 times and counting how many heads I get. So this scenario, this simulation, this is what we call a box model or a probability model. It says, if I draw this box 10 times, that's the same thing as flipping a coin 10 times. So we're going to simulate these different scenarios with drawing tickets out of a box. And you might be wondering, why am I doing this? What is the point? And with a coin, we probably don't need to do this. But as our situations get more complicated, like say we have a whole population and we want to randomly sample people, the box model analogy is super helpful. It helps us calculate statistics. Kind of like with conditional probability, right? The very last thing we did on exam 2 was these conditional probability tables, like this. And I told you guys the table helps us answer the questions. It's kind of the same thing in exam 3. The box model is going to help us answer more complicated questions. But chapter 13 is just about getting comfortable making them, because it's kind of weird. It's kind of a weird thing. You've probably never done anything like this before. And so that's what we're going to be doing for a couple more examples, and then we'll actually look into, okay, what statistics can I calculate based on this? So what else do I have? It says statisticians use the term random variable for variables whose values are based on the outcome of a chance process. So now we're talking, in exam 1, we talked about one variable. Exam 2, we talked about 2 variables, the correlation, the relationship between 2 variables. And then exam 3, we're talking about random variables, variables that are generated by a chance process. So it's like we're taking everything one step further. So in this case, the number of heads is the random variable because it changes depending on the luck of the draw. Random variable. So like if every single person in this room flipped a coin 10 times and counted how many heads they got, we would all get different numbers. Some of us would get 5. Our numbers would range from 0 to 10. And we could make a distribution. We could make a histogram of all of our outcomes if we all did that. So that's why that's the random variable. It changes every time you flip the coin 10 times. Let's do this second one. It says create a box model for counting the number of 2s that appear in 20 rolls of a fair die. So let's see. I want to think about my hint. Rolling a die 20 times is confusing. There's so many different outcomes I could get. So let's think about the hint. It says start by making the box for a single draw. So I'm going to draw my box for one roll. Okay, it's like probability. Take something complicated and make it simple. And then this is going to help us. So if I roll a die once, I have 6 outcomes, right? I can think of my sample space for rolling a die once. So my box is going to have 6 tickets for a die, right? Just like for a coin, if I flip a coin once, I have 2 outcomes. So my box here had 2 tickets. And what goes on, if I look here, so I have a box with tickets. Each ticket has a number. So here I used 1 and 0 because what I put on the tickets is based on my random variable. I wanted to count, did I get ahead? Yes. Or did I get ahead? No. So it's kind of the same thing here. My random variable is actually the number of 2s that appear, right? That's my random variable because if all of us rolled a die 20 times, counted how many 2s, we'd all get different numbers, right? It changes. And so this is kind of like this one, right? If I get a 2, I want to count it as 1, 2. If I get any other number, I want to count it as 0 2s. So just like here, 1 head, 0 heads. So I know I'm going to have 6 tickets. Let's see. Here's the 6 of them. But I don't necessarily want to put a 2, like 1, 2, 3, 4, 5, 6, because I'm counting, did I get a 2 or not? So if I get a 1, I'm going to count it as, nope, I didn't get a 2. If I get a 2, yep, I got 1. And then the rest of these are not getting a 2. So because my outcome is yes or no, 2 or not 2, head or not head, that's when you're going to use the 1 and 0. Because if you get a 1, that's counted as 1. If you don't get what you want, that's counted as 0. Because otherwise, like if I had 1, 2, 3, 4, 5, 6 on here, if I got a 6, I'd be counting that as 6 2s. It doesn't really make any sense. So I would go ahead and say that so we did our box, we did the tickets. The tickets correspond to the random variable, what number's on them. How many draws to be made? Well, this is for 1 draw, but I want 20 rolls. So if I want to simulate 20 rolls, I would draw out of this box 20 times. Again, with replacement, just because the die, it never changes. Your probability should stay the same every time. Your chance of getting a 2 should be 1/6 every single time. So I'm going to draw 20 times with replacement and take the sum of my tickets. And then you can see this box it's a little tedious. We can actually shorthand write this by saying, okay, my box I know has 6 tickets. There's 1s and 0s, so I have 1s, I have 1 1, and then for the 0s, I have 5 0s. So that's another way. Sometimes you'll see the boxes written out like that just because it makes it easier to draw. But the numbers above the tickets, indicate how many of those tickets there are. So indicate how many are in the box. So I'm looking at, did I get a 2? Yay. Or did I get a 2? No. And then this box model is going to help me answer questions about this scenario. And these two things are equivalent. They're basically the exact same thing. Yeah?
So just by doing this, we're not answering the 20-row question.
So just by making the box model, yeah, we haven't said how many 2s are we expected to get in 20 rolls. That's what we're going to look at next. Now we're just saying, how do we actually draw the box? Okay, we'll do a few more. I'll let you guys try a few as well. They get a bit more complicated, so I want to do a lot of examples for you guys. Number 3. Let's see, number 3 says a multiple choice test has 25 questions. Each question has 5 answers. Suppose you guess at random on each question and your number of correct answers is counted. What is the box model? So I always like to say when I first read these questions, okay, what am I looking at? It says your number of correct answers is counted. So you can think if everyone in the room, if everyone in the class guessed on a multiple choice test, we could look at their number of correct answers, and that's what would be different for all the people. So this is my random variable. It's based on the luck of the draw. Okay, sometimes actually whenever I upload your guys' exam scores, I can figure out, you guys can figure it out too, but we can figure out how many, my test had 70 questions. If you just guess on every single question, how many are you expected to get right? And sometimes if people have lower than that amount, I know there's a problem. I'm like, okay, they must have gotten graded with the wrong form, or they're not in the class and took my exam randomly. There's something weird going on if that's the case. Honestly, even if they're not in the class, they shouldn't get too far below what you would expect by guessing. So what is the box model? The test has 25 questions. So this number is n, is what we're going to refer to as n. So it's our number of times that we're doing something. So if I look back, I guess I should have said this on the other page. If I look back here, for this one right here, the 10, that was my n. 10 was n. Here 20 was n because we're doing 20 rolls. So in statistics, we represent that with the little letter n. So 2 things to look at first. What is your random variable, and then what is your n? Because the random variable is going to tell us what goes on the tickets. So my box model, I want to think about my hint, right? If I think about 25 questions, each with 5 answers, that's too confusing. That's like 100 different possibilities. It gets kind of crazy. No, more than 100, 125. Oh, I don't even want to think about that. Let's just think about one question. So my hint was to always draw the box. Always draw the box for a single draw. In this case, since I'm dealing with a multiple choice test, one question. So that's the thing. I feel like if there's something about this that confuses students is they always think about, oh, let's think about all the questions. No, don't do that. Just think about one. Question. Yeah, sorry. For example, 20 rolls is the n. Yes, on this page, 20 rolls is my n, and on example 1, 10 tosses is my n. All right. So for one question, if I just think about one question, that will tell me one question. That will tell me how many outcomes there are, how many tickets there are in my box. So like, for example, 2 was one roll of the die, which has 6 options. Here it's one question, and it says each question has 5 answers. So if I wanted to simulate guessing on one question, I would make my box have 5 tickets. Because it's too complicated to think about all 25 questions. I'm going to have a ton of tickets in my box. Let's just think about one at a time, and then we can say we'll draw out of the box 25 times. So I know I have 5 tickets. Let's see, 1, 2, 3, 4, 5. And then what goes on the tickets is, again, it's your number of correct answers. So we're counting, just like the other 2, we're counting, did we get an answer correct or no? So if I get the answer correct, I'm going to count it as, yes, I got 1 correct, right? That's how I score your guys' exams. If you get a point correct, you get 1 point. If you don't get it correct, you get 0 points. So let's just assume it doesn't say there's any funny business going on. So let's just assume there's 1 correct answer and 4 incorrect answers. I could also draw this box if I wanted to. I could use the shorthand version. I could say there's 1s and 0s. There's 1 1 and 4 zeros. So 5 tickets. Remember, a box model is just a probability model. Looking at your box, you should be able to tell what's the probability of getting a correct answer. 1 out of 5, right? Same thing with this other one over here. Box model is just a probability model. If I look at my box, I should be able to tell what's the probability of getting getting a 2, 1 out of 6. Same thing up here. What's the probability of getting ahead? 1 out of 2. So it's really just, it's tying together probability and then the idea of random variables. So back to this, I would have to say, so I drew my box. We have to specify how many times we draw. So I would say I would draw 25 times to represent 25 questions. Right? Because I would draw once for one question. And then the question is, oh, this is a good question for you guys. I'll ask this as an iClicker, but I don't have this as an iClicker, so I'm going to write it over here. Should I draw A with replacement or B without replacement? So if this represents one question, if I draw a ticket out of there, I either get the answer right or wrong. Should I put it back in before I draw again? So if you're just guessing on 25 questions, should I draw with or without replacement? So A is with, B is without. So I'll give you guys a minute to think about that. That's easy to remember, right? A with, B without.
Is it over?
Not yet. The moment of truth. Okay, 70% of the class said with, 30% said without, and some jokester put D. Who are you? Stop messing up my data. Okay, so the majority says with. Let's think about this one. Majority says with, so if you guys are team with, you're basically saying that if you get a correct answer on your first draw, you want to put that back in so you can get a correct answer on your second draw. And that's exactly correct. If we would draw 25 times without replacement, we'd run out of tickets, right, after 5. Then on the 6th one, we'd be like, what do we do? So it definitely should be with replacement because we want our probability every single time we draw of getting a right answer to be 1 out of 5. Yeah?
So is it as simple as saying because every question has 5 answer choices?
Yes, that's true. He said, is it as simple as saying because every single question has 5 answer choices, we want to be with replacement. That's exactly right. Yes. All right, let's do number 4. So there's 2 more. Yeah, 2 more. Let's do 4. This is a great one. It says a roulette table has 38 slots. If you bet $1 on red and it comes up red, you win $1. Otherwise, you lose $1. What is the box model for? Here's my random variable, your total winnings. Playing roulette 50 times. So my random variable, anytime you're gambling, the thing that changes depending on the luck of the draw is your winnings, right? Gambling, you don't know if you're going to win or lose. And in this case, what is our N? So how many times are we playing roulette? 50, good. I heard a bunch of people say it, right? So 50 is our N. So we're playing roulette 50 times, but let's not think about that. That's a lot of gambling. Let's think about playing roulette 1 time. This is a question too. How many of you guys have played roulette? Has anyone played it before? Only a few. You guys probably aren't gambling very much, which is good. Okay, so in case you don't know roulette, in the stat department, we have a roulette wheel, and I brought it to class. So here it is. It's a little one, but it gets the job done. Is that all I can zoom out? You guys can see it, right? Here's the roulette wheel, 38 slots. You can either bet on red, you can either bet on the colors or you can bet on the numbers. Your chance of winning for the colors are a bit higher than the numbers because there's no duplicate numbers. But I've actually never played roulette in real life, but maybe someday I will. But for now, we're going to play roulette not in real life. So basically how it works is there's a marble and you bet, like, what did it say? We're betting on red? Yeah. If you bet $1 on red and it comes up red, then you win $1. So basically what you do is spin. You spin the roulette wheel and then you put the marble in. Oh, I won. Yay! Okay, so it came up red, so I'd get $1, is how it works. And we can look at the probability you win, probability you lose. But if we play 50 times, what are we looking at? Your total winnings. So I'm looking at, did I win $1 or did I lose $1? And more on this later. I just wanted you guys to see what it looks like. But that's the roulette wheel. So if I wanted to simulate a box model, because I'm guessing I don't actually know anyone else in my entire life that owns one of these, so it's complicated to think about all at once, but we can use a simple box model to answer questions about probability. So I would say, I'm going to say, I know I keep saying this over and over again, but I'm going to say this again, that we want to draw the box for one spin. All right, so I'm going to, this one's more complicated than the ones we've done. I want you guys to try to draw it yourself, and I'm going to ask, we'll do it together at the end, but I'm going to ask one question. If you were going to draw this box, so here's my box, how many tickets go in the box? Okay, so I said draw the box for one spin. So iClicker says, that was my next question, how many tickets are in the box? So given all that info in example 4, if you were going to draw your box, and if you know, go ahead and draw it. Try and draw it and see if you get it right. But how many tickets are in the box? So you guys can debate that for a bit. Most people said C. That looks good. Some people said D. Oh, E. Okay. Who are you? So C, that looks great. 38 tickets, right? Because one spin, there are 38 slots on the roulette wheel. Just like one roll of the die, there's 6 options. One multiple choice question, there's 5 options. So 38 tickets, which is kind of obnoxious. I do not want to draw 38 tickets. That sounds horrible. So let's take a look at our random variable. What is on our tickets? Can I do something like this? And so I just want to know, this is a probability model, I want to know what's the probability of winning. So it says if I get a red, then I win. So I know that there are 18 reds, so my chance of winning should be 18 out of 38 is what I should see from this probability model. So your total winnings, I can either win $1 or lose $1. So I know my tickets are either going to be winning $1 or the only other option is losing $1. And here I'm not, if it said, what is the box model for counting how many times you win? Then I could do ones and zeros, right? You either win a success or you lose a failure. But I want to know my total winnings. And when I lose, I don't just get $0, I lose $1. So that's a key aspect to this problem. You don't just get $0, you actually lose $1. But if I leave it like that, it looks like there's only 2 tickets. So I have to say how many winning tickets there are, all the reds, which is 18. So this is good. My probability model says the probability I win $1 is 18 over 38. And then the rest of the tickets are losing. So there's 18 black and 2 green. So there's 20 losing tickets. So this is how those casinos, they get you, because 20 out of 38, the probability of losing is higher than the probability of winning. So this is, if I draw one time out of this box, that simulates playing roulette. There's 38 tickets, there's 38 slots, there's 18 wins, and then the rest of them are losses. So I would say my N was 50, so I would say I would draw out of this box, draw 50 times. Again, I'm going to say with replacement because the roulette wheel never changes. You can't take a slot out of the roulette wheel. So even if I win the first time, I want to have the same probability the second time I play. So I'm going to say draw 50 times with replacement and take the sum of my tickets. And that will add up how much I win or lose. And that looks good. I got this basically from, it says, if you bet $1 on red and it comes up red, you win $1, otherwise you lose $1. So that's where my total winnings came from. Let's do the next example. It's also a roulette table. So if you're playing roulette, your box is always one spin. You're always going to have 38 tickets, which is nice. This time it's saying, what if we bet on the number 7 and it comes up 7? Then you win $35. Otherwise, you lose $1. So higher risk, higher reward. If I was playing roulette, now I'm curious. I just want to see really quick. Let's see if I win. I'll bet on 7. I would bet on 7, so I'd spin it, and then if it lands on 7, I win $35. Nope, it landed on 4. Okay, good. Otherwise, so my chance of losing is, there's only one 7. So my chance of losing is actually 37 out of 38, right? Because there's one 7. Where is the 7? It's somewhere on here. There it is, right there. So I should have lost there. The probability was against me. But if I was going to draw this box model, I would, again, draw for one spin. My random variable for gambling is pretty much always going to be your total winnings. So that's my random variable. If all of us bet on the number 7, some of us would probably win. Most of us would probably lose. I'm playing 100 times, so that's my N. And my box model, I said, is going to have 38 tickets because it's roulette. So I'm going to draw for one spin. There's 38 options. And this time, it's not that I win $1 and lose $1. It's either that I win $35, so I win $35, or lose $1. So my random variable tells me what goes on my tickets. And then I have to say, okay, what's the probability of winning $35? So that's if I get a 7, and there's only one 7. And then the chance of losing $1 is 37. 37 out of 38. And you'll notice here, actually, the fact that I'm betting on 7 doesn't really matter, right? The fact that it's the number 7, I could be betting on 1 and the box model would be the same. What matters is the probability of getting a 7 is 1 out of 38. The fact that it's a 7 is kind of, it doesn't matter. I could say if I bet $1 on the number 35 and it comes up 35, then I win $35. The box model would still look the same because it's just a probability model. What's the probability you win? What's the probability you lose? So I would say here again, I would draw, this time I'm playing 100 times, so I would draw 100 times with replacement and take the sum of my tickets to see how much I won after playing 100 times. If I did that, that's the same odds, same probability as playing roulette 100 times and counting how much money you win. All right, so that's all fine and dandy, but what can we ask about this? So now that hopefully you guys are at least a little bit more comfortable drawing these box models, let's look at how to find the statistics. So what am I actually expected to win over time? If I play 100 times, what am I expected to get? And then what's kind of the give or take? It's better, we said before, it's better to make our prediction be a range, so we're gonna use the same kind of idea. But on the homework that's due on Thursday, I hardly ever talk about these summary pages, but I'm gonna star this one and say to consult while doing homework. If you're confused at all on the homework, this should help. These 3 things. Remember, if you're confused, you're probably forgetting to make the box for a single play. So only think about doing the thing once. You definitely want to know what is your N, how many draws should there be, so how many times are you actually doing the thing. And then this is the key. It says the draws are always with replacement for gambling games because everything that we've been working with gives you the same probability each time. So that will help on the homework. Come back to it for sure. But let's go to the next chapter is chapter 14. So we'll look at our first two statistics in chapter 14. All right, so chapter 14 is called the expected value and standard error of the sum. So all of chapter 13, I said we're going to add up our tickets, take the sum. So what are we expected to get? And then standard error is like standard deviation. It's a measure of spread. So expected value and standard error are also known as EV and SE. And those are the two statistics we're going to work with a lot in the upcoming weeks. So it says in part 2, descriptive statistics. So this was back exam 1. When we first looked at descriptive statistics like average and standard deviation, it's telling us we summarize the list of numbers by looking at the average and the SD. And graphically, we drew a histogram. So we did that back in the day. And then that was exam 1. And then exam 2, we looked at our numbers by looking at we looked at two variables. We looked at averages, standard deviations, correlation, and graphically we used a scatter plot. Now on exam 3, we're going to do the same type of summaries for numbers generated by a chance process. So random variables. So we're going to do the same kind of thing. Look at measures of center, measures of spread, and then graphically see what they look like. So it says, given a set of n draws from a box, we might be interested in sum, average, and percent. So for sums, the most common thing for sums to look at is anything that's like a gambling game. Because you want to know, add up how much money you win and lose, what is your total outcome. Average and percent are more common. We're going to look at these later. These are common in polls or surveys. Right, I give you guys a lot of surveys. We like to look at averages, what percent of the class does something, what percent of the class believes something. So we're going to focus, let's see, we're going to focus on the sum first, and then we're going to switch gears and talk about average and percents. It says in the next chapter, we'll talk about those other stuff. But the biggest thing is that we're going to look at these two statistics, expected value and standard error. So the expected value is like the average. And then the standard error is like the SD. So expected value is what we're expected to get. And then the standard error is like the variability, the give or take. And the reason we're, instead of just using average and SD, why am I not just sticking to what we already know? Well, with random variables, they're different. It's not just a list of numbers. It's numbers that are generated by a chance process. So these are the statistics that we use, but they're pretty much analogous to what we've already done. So let's do, how do we find them? So we know how to find average and SD, but how do we find expected value and standard error? So they're both based on average and SD. So let's take a look at the formula. Actually, let's see, what does all this say? Okay, this is actually pretty important. It's telling us the sum of n draws from a box will vary because every time you draw n tickets, your sample changes depending on the luck of the draw. So every time I do a chance process, there's some element of chance, variability, randomness, and we don't know what we're going to get every single time. So here's the deal. It says we need some way to quickly describe the distribution of possible sums. What would you expect it to be and how far off? So that's the expected value and standard error. So it's like we want to know if we do a chance process over and over again, draw tickets out of a box, what are we expected to get and what's the give or take? So the expected value, the formula is not too bad. I'm just going to write it right here. The expected value for the sum, because we're specifically looking at sum, is just right here. It's n times the average of the box. So this is our first new statistic. And expected value is like the average. It even has the average in the formula. But it changes depending on n, right? So for example, let's see, example 1, it says 100 draws are made at random with replacement. From this box, there's 5 tickets. Pretend this is a box with tickets. And we are going to draw 100 times. So my question for you guys is, we don't even need to know, I guess we don't need to have any knowledge about statistics to answer this question. If you draw out that box 100 times, what's the smallest sum that you could get? So if you drew 100 times and added up all your tickets, what is the smallest possible sum? I'll give you a hint. The smallest sum, that is not very probable. Like this probably would not happen that you would get this sum, but it is possible. So going back to the eye clicker, I want to see if you guys can get this before I even say anything about it. So think about it. Talk to the person next to you. I bet someone in here knows the answer. Okay, I'm going to stop. Spend 1 minute. The smallest the sum could be, you guys said, yay, see, that looks good, right? The smallest possible sum will be getting the smallest number every single time, which is not very probable, but it is possible, right? Anything's possible. So this answer would just be getting, the smallest possible sum would be getting all ones, which would just be 100, right? 1 times 100. The largest possible sum would be getting the biggest number every single time, all 5s, which if we're drawing 100 times, 5 times 100 is just 500. So I know every time I draw 100 times and take my sum is between 100 and 500. But there's a lot of other options in between those two numbers. So this is the relevant question. What's the expected value of the sum? And we said the formula is n times the average of the box. So n in this case is 100, right? We're drawing 100 times. So 100 times, and then the average of the box, this is really nice. We already know how to find an average, right? We're just going to add up all these tickets, divide by 5. So the average of the box is literally just the average. Treat these tickets as a list of numbers. I can just take 1 plus 2 plus 3 plus 4 plus 5 over 5. 3, that looks good. So my expected value is 3 times 100, which is 300. So if I draw out of that box 100 times and add up all my tickets, I'm expected to get a sum of 300. So that's not that exciting. That's kind of boring. Let's actually do, let's do a better example. Let's do number 2. Number 3 is probably the best one. We'll do number 2 as well. It says a die is rolled 100 times and the sum of the number of spots appearing on each roll is computed. What is the expected value of the sum? So I know the expected value of the sum is just n times the average of the box. The formula kind of makes sense, right? Like you're expected to get the average every single time, so it's n times the average. That's where it comes from. So n in this case is a die is rolled 100 times. My n is 100. 100 times, and then I guess I should draw my box here so I can figure out the average. So remember, anytime you're drawing a box, you want to draw it for one single roll. We're rolling the die 100 times. Let's ignore that. I want to draw my box for one roll. So hopefully if you guys take away one thing from today, it's just to remember to think about doing the thing once, and it'll help you. So if I roll a die once, I have 6 possibilities. We've done a box for a die before. We know there's 6 tickets. And then I need to decide, what do I put on the tickets? So the one we did before, we put ones and zeros because we were counting how many twos we got. Here, my random variable, let's see, what am I looking at? A die is rolled 100 times, and the sum of the number of spots appearing on each roll is computed. So what I'm interested in is every time I roll, what is the number of spots appearing? So that's going to be my random variable. So like if I roll a die once, I can get a 1, 2, 3, 4, 5, 6. So if that's what I'm concerned about, the number of spots, if I get a 1, there's 1 spot, right? If I get a 2, there's 2 spots. If I get a 3, there's 3 spots, 4, etc. So here, I'm not just concerned, did I get a 2 or not? I'm concerned, how many spots did I get? So your random variable, it's always good. Like I said, the first thing I always do is say, what's n and what are we looking at? What's our random variable? It tells you what goes on the tickets. So this box looks good. I can easily figure out the average by adding all these tickets up. 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. And then now I know my sum is expected to be 350. And I know the smallest my sum can be is getting all ones. That's going to be super rare, but it could happen. So all ones would be a 1 100 times. And then the biggest it could be is all sixes. It'll be a 6 100 times. So I want to do a bit more of a complicated example. Let's do number 3. And then, we're going to do number 3. And then I do want to, I guess before we even do number 3, I want to mention the standard error, because I don't think I've talked about that yet. I just talked about expected value. So for standard error, basically what it is the standard error, I said, is like the standard deviation. It says the sum of the draws from a box will be around the expected value. But again, the expected value is such an exact number. That's what we're expected to get, but we might not get that every single time. So it's better to give a range, give or take chance error. And it says the chance error is given by the standard error. So if you guys see this, here's the formula. I'll go ahead and write it. The standard error for the sum, because right now we're just working with sums, is actually, it's the square root of n times the SD of the box. So that is going to be the formula for standard error. It's like the standard deviation, but it's based on n. The reason the square root is in the formula has to do with something called the square root law, which I'm guessing most of you guys probably don't care about. But if you're curious about it, ask me. I have the proof for it. It might be in the back of the book. If not, it's on our website. But this is the formula for it. So knowing that, let's just go back here really quick. I want to do number 3. It says, you bet $1 on red 76 times in a row in roulette. So n is 76. It says again, this means that if the ball lands on red, you win $1, otherwise you lose $1. What is the expected value of, here's my random variable, your winnings. So with this one, we already did this box, right, for betting $1 on red. It says, remember, there are 18 reds, 18 blacks, and 2 greens. So this one, I guess I'll go ahead and draw the box again because I'm going to need it. We said we would draw the box for 1 spin. But we already drew this box, right, in chapter 13. We said, well, if we're spinning the roulette wheel once, there's 38 tickets, 38 slots. Those are all of my options. And I can either win $1 or lose $1, right? My winnings, that's what goes on the tickets. And then the probability of winning is there's 18 reds out of 38 tickets. And then the probability of losing is 20 out of 38. So this is the same example. The reason I went so fast on this is because it's the same example from before. But they're asking us, what is the expected value of the sum? So n, I know, is 76 in this case. And I can even say, before I figure out what this number is, what am I expected to win, I can say right away, we'd actually expect to lose. We'd expect to lose, right? Just looking at this box, because there's more negative ones than positive ones. So we'd expect to lose. The question is, but how much? But how much if we play 76 times? And we're super close to answering that question. So that's the expected value. What are we expected to get? To find the average of the box, let's see. So I need to find the average of the box. This one is a bit more complicated than just, like, this box is pretty straightforward, right? 6 tickets, you add them up, divide by 6. This one has 38 tickets, though. So essentially what I want to do, if I drew out this box, like, I don't want to do this whole thing, but really this box has 18 ones, right? So 1, 1, 1, 18 ones, and then 20 negative ones. So there's a bunch of different tickets. And then there's 38 total. So essentially what I'd want to do is add up 1 plus 1 plus 1 plus 1 plus 1, 18 times, right? Add up all the 18 ones. So I would say there's 18 ones. If I add them up, I get 18. Plus there's 20 negative ones. So I do negative 1 plus negative 1 plus negative 1 20 times. And then there's really, I only see 2 tickets here, but really what this represents is there's 38 tickets. So anytime you calculate an average, you add up all the numbers and then you divide by how many numbers there are. So there's 38 tickets in here, 18 ones, so I do 1 plus 1 plus 1 plus 1 18 times, and then 20 negative ones. So negative 1 plus negative 1, etc., 18 times. And you guys know I like fractions. I'm just going to leave this as 18 minus 20, so negative 2 over 38 is the average of the box. Honestly, the fractions make it easier to put this answer into ln kappa, because when I do this math, I know it's going to be exact because I use the fraction. So I would, let's see, what do I get? 76 times negative 2 over 38. Oops, can you guys see that? It's kind of hard to see. Negative 4? Yeah. Negative 4 is my answer. So it says right here, what's the expected value of your winnings? I'm expected to lose $4. So that kind of sucks. But the question is, give or take what? I'm not always going to lose $4. So if I wanted to find the standard error, I told you guys the formula's over here, right? It's this, square root of n times the SD of the box. What I'm going to do on the homework, so like here, if I was just looking at this example 4, a box contains these tickets. What's the expected value in standard error for the sum of 25 draws? So on the homework, I'm going to tell you guys, we already tested on calculating standard deviation. The way you find the standard deviation in the box is just treat these as a list of numbers and find the standard deviation like we did in chapter 4. But on the homework, you'll notice that I actually just give you guys the SD. So I would say, okay, the SD here is 2.
Would you do that on a test?
I do that on a test too. If I wouldn't make you guys find SD by hand just because, again, we already tested on that. No need to do it again. So if I was going to do this, if I wanted to find the expected value and standard error for the sum, with the expected value, that's just n times the average of the box. So n in this case is 25. The average of this box, I don't know what it is. Let's see. We'd have to add all these numbers up. The average is going to be 1 plus 3 plus 4 plus 5 plus 7 divided by 5, which is 4. So that's a really easy box to find the average of. Average is 4. So 25 times 4 is 100. So that's telling us, okay, if I draw out of this box 25 times, I'd expect the sum to be 100. But now let's add this idea of the give or take. The standard error for the sum is square root of n times the SD of the box. And the nice thing is we already know n is 25, and the SD will be given to you guys on the homework. So here I gave it to you, it was 2. So square root of 25 is 5 times 2 is 10. So the way I'd interpret this, expected value give or take standard error, I'd say we'd expect to get a sum of 100, give or take 10, if we draw 25 times. So that's a better estimate, 100, give or take 10. So we'd expect to get between 90 and 110 as my sum if I draw 25 times. So the standard error allows us to give a range, which we know is better for making predictions. And this is all about uncertainty. So there's a lot of error, a lot of predictions that we have to make. Standard error helps us do that. It's a measure of the spread of this. So I think that's it. If you